Thank you. Thank you, Andres. Thank you, all of you. And yes, I'm going to talk about this different perspective. That is essentially, when can we do things tractably, which means exactly and efficiently. And part of what I'm going to show you is taken from some materials or from some tutorials and other talks that I give with some colleagues, especially Robert Pearts from TU Graz, Yujang Choi from Arizona State University, and He van den Broek from UCLA. Okay, and I am Antonio. So, hi. I run a lab in Edinburgh, and this lab is called April. It's a very flexible acronym that I use for essentially shape the topic of the talks I'm going to give. So today is going to be essentially about probabilities, integrals, and logics. And these are the three ingredients that I will try, especially in the second part, to put together to craft some challenging reasoning scenarios, where models, generative models, are asked to perform reasoning, but they also need to deal with logic. And we have to deal with integrals, and hopefully we can try to compute them exactly. Okay? So, in a nutshell, what I'm going to talk about is going to say, can we take some of the pieces of deep learning to build generative models that are still able to perform reasoning, that is probabilistic, also logic, in a way that is flexible enough and reliable enough, such that we can deploy that in trustworthy machine learning systems, okay? So this is going to be the general topic for today's talk. But secretly, it's also going to be just a big, long love letter to mixture models. They are super nice, they're amazing. And I hope you're going to see and appreciate some aspects of mixture models that perhaps you didn't know yet, okay? Or you didn't see also during the previous talks in this super nice summer school, okay? But let's go back to reasoning. So here are some real-world scenarios where reasoning might really matter, right? And so these are some sort of like three showcase applications for where we might need reliable and efficient systems, okay? I'm going to use them as three running examples throughout the talk. So hope I can get them correctly. Interrupt me anytime if you have questions or if anything is not clear, please, okay? So in the first scenario, we might have like a very simple machine learning system deployed, some healthcare application, when you have to deal with records with patients, okay? And then you might have measured something for that patient, but some of these other features or records might not be available for a specific patient, okay? So some information is missing, you might not have access to that, and you have to deal with that. The probabilistic recipe for that will be, let's try to marginalize this out, okay? And then try to understand what's the probability of giving a treatment to a patient, or what's the probability of this condition just by having this missing information, okay? Having unavailable records. In the second case, this is your bank essentially deciding if giving you a loan or not, right? And by some regulation, for example, from the European Union, well, if they employ some classifiers or machine learning systems, they better be fair, right? Where fairness, in a sense, is defined on the fact that the prediction that the classifier the bank is employing should not change, should not depend, actually, on some certain sensitive attributes, like the race, the gender, the age, and things like that, okay? So we would like to essentially understand and reason about the behavior of a machine learning system with respect to some fairness attribute, okay? And the third one is cast here in the context of self-driving cars, but can be cast like in many other contexts, and essentially says, if you have a classifier, right, and you want to deploy it, and you want to make sure that the classifier is safe, can you certify that actually there are no adversarial examples where that are going to disturb the decisions taken by the classifier, where adversarial examples are defined as those, let's say, minimal perturbations of the input that are going to dramatically change the output of the classifier, okay? So if we have this machine learning system that's deployed, can we really say something, can we certify, right, with 100% guarantee that this output is not going to get corrupted by certain kinds of adversarial examples? Okay, so these are like three scenarios when I have machine learning systems, and I would like to reason about the behaviors of these systems. And I want to do that because reasoning about the behavior of the systems builds trust over the system, and in a certain sense, make me want to use them, or make like the user look into them and understand what can go wrong, right? And perhaps this can be fixed later, okay? But how do we operationalize this, okay? These are three kind of like high-level reasoning scenarios, but we need to make them, shape them, formalize them such that we can get some quantities, right? Something we can compute, something we can talk about in a precise way, right? So this is where like probabilities come into play. You have already seen this through other examples in this course. And then essentially, if we apply probabilities and try to formalize them, we might come up with certain mathematical expressions that involve probability distributions. And these probability distributions are essentially encoded in our machine learning systems, okay? So here are three possible formalizations. There may be many more. One is a simple integration. When we have missing values, we would like to marginalize them out, right? So these are my values, my features, my records that are missing for some patient, and I just want to marginalize them out, computing a big integral or a big summation here. Well, for the fairness case, there are many metrics defining fairness. Here is like a very simple one. Essentially says that if one of your attribute here, let's say this XS, is your sensitive attribute, let's just assume it's binary for the simplicity, then essentially the expected output of your classifier, when you observe all the other features, should not change much with respect to the other scenario when we set or we see the attribute to be on the other value, let's say 1, okay? So I would like to compute this difference, and this difference should be hopefully 0. For the adversarial robustness, instead, this is a definition that goes under the name of adversarial smoothing. So if this is like your classifier, and this is the generic input the classifier takes, if I corrupt the input by adding some additive noise, right? And let's say this noise comes from some Gaussian distribution, for example, well, if I'm able to compute this expectation here, then I can create a new classifier, and this new classifier is going to guarantee to be robust to perturbation that live essentially in a ball that has a radius depending on the variance that I am observing, and this might be good enough for certain applications, okay? So 3 different cases where 3 different reasoning scenarios can be formalized in 3 different mathematical expressions that, however, do contain some very common ingredients, right? And namely, computing expectations or big sums, dealing with probability distributions, but also with other machine learning systems, let's say classifiers, okay? So these are the 3 running examples I'm gonna use throughout the talk. There are more than this. I'm going to talk in the second part about neurosymbolic systems, where we do have probabilities, but we also have like logical statements coming up in the form of requirements, something you want the system to abide to, something that the system needs to do 100% of the time. But you have already seen that these kind of expressions also pop up in other scenarios that you have seen throughout the course, right? When computing other quantities for Bayesian inference or for probabilistic programming. So these mathematical expressions involving big sums, integrals, probability distributions, and other functions are ubiquitous, right? So how can we deal with them, right? In a certain way such that we can compute them efficiently and reliably. And why do I want to do this? Because in general, well, you have already in your toolkit lots of nice algorithms and tricks to approximate them, okay? Just this morning, you've seen like the wonderful world of Monte Carlo and sampling, okay? And that's one way, for example, to do that. But in some scenarios, this might not be the best thing to do. And why is that the case? Because it might be even more expensive to try to do that than just trying to understand when you can impose some structure over these distributions and over these classifiers to actually get an exact result. Or in some other scenarios, you just want like the exact result because you want essentially to have an exact solution, or you want to bound the error that you're going to commit in a hard way. Why do you want this reliability? Because in some example, in some scenarios, safety might be important. So you're not just interested in computing some approximate kind of quantity that tells you that your system might or might not behave in a certain way. if you want to peek into the behavior of the system, you would like to get like a metric that is faithful to the behavior of the system. So the quantity that's outputted by the system truly reflect what the system is going to do, even if this is a probability. So an exact probability is better many times than an imprecise probability or an approximate probability. Okay, so this is like the scenario. We won't like to do this, and we would like to do this also in something that's called here polytime, which is a very broad perspective. Might mean something, but might mean also nothing. Generally, it should be like efficiently, right? Or as fast as possible, okay? But if I combine these two words together, exactly, and polytime, essentially this is the recipe for tractability, okay? So whenever you hear tractability, when someone is saying like this should be something that we can compute tractably, it's a function, then essentially means you can compute the function exactly and in polynomial time. Okay, let me be just a little bit more precise over this. So here's a definition. It's a boring definition, but this is, I promise this is the only boring slide. So, but I think it's important to go through that to set like the basis, okay? So essentially it says like if we have a model class, and the model class is essentially your system, you abstract away from just the set of parameters that you might have learned or set somehow, right? You have a model class. For example, you have a neural network or a computational graph that is built over certain ingredients. That's your model class, right? And then if you want to ask a query to the system, and then you have many possible queries coming from families of queries. And queries are essentially just the mathematical expressions that I showed you before. So I already gave you 3 examples of queries for the different scenarios. Okay, then if I fix like my model class and then I fix like my sort of like query class, no matter which query, if I change this slightly, for example, I pick like some attributes from the patients to marginalize over or some other attributes, they're still like instances of the same class of queries, which is marginalization queries, okay? If I change a bit the fairness, but the mathematical structure of the query is the same, it's still like the same, okay? And if I pick something like that, then what I want is that all these queries I can compute exactly over my model and in time that is polynomial in the model size. So with this weird notation here, with the bars, I mean like the size of the model. So what's the size of the model? Well, we need to agree on some computational model. But let's say I'm looking at the computational graph, right? And the graph that I'm going to talk about in this talk are super simple computational graphs made of a bunch of like sum and products. So the size of the model is going to be the number of edges in my graph, okay? Which basically says like how many operations I'm going to compute to output the number, which is the result of the query, okay? Which is going to be the number that reflects the behavior of your system. So definitely this is something that is model-centric because it really depends on the model class that you pick, but at the same time is also like query-centric. So we can say that something is tractable only with respect to a certain reasoning task that we have in mind. For so one inference scenario, one family of queries, okay? So this is important. So sometimes we approximate this and say, well, this model or this algorithm is tractable, but it really depends on what you want to compute, okay? So many model classes, as we're gonna see, might be tractable for some scenario, some inference scenario, but not for others, right? And the true art is really understanding what is tractable for what. Okay, well, here it just says polynomial time. This is because like computer scientists like polynomial with respect to exponential. So exponential is very bad, polynomial is good, but then a polynomial, even if it's quadratic, cubic, or to the power of 7, still a polynomial, but not be what we want in machine learning these days, right? So we really want this to be actually linear in the model size. And for the 90% of the talk, this is actually going to be linear in the model size, okay? So something that you can just compute in a feed for forward pass of your computational graph. And then just like some minor note here, for those of you who are computer scientists at heart and say, well, I know what you mean, but what happens if like the model size is actually exponential in my domain, right? It's still gonna be linear in the model size, but the size is exponential, and that is much less interesting. So in that scenario, of course, we don't gain anything, but in this case, for whatever we are gonna talk about today, this is sort of like given, okay? Because we build the structures, we learn the structure from data, and therefore we know how to govern the structure and to have a structure that is large enough that we can saturate the memory of our GPU but not large enough that we're going to wait for the universe to decay before like being able to compute this query, okay? All right, so this is the boring slide. It's just there, you can forget about that, but if at a certain point you need to understand what's tractability and be a little bit more precise, you can check like the slide over in the repository of the course. Okay. Again, why do we want exactness? Because exactness gives us like 0 error, right? And that's the highest form of guarantee. But some other time you can still bound the error, and that's still a very valid guarantee, and that's still very reliable, if the bound is meaningful, of course. Okay, later we're gonna see, for example, this in the case of like neurosymbolic AI, and reliability in that context means that if your model, your neural net predicts something, but this something violates a safety constraint, then you should never be able to predict that actually in the first place, okay? And of course, you want to bound the error because if you need to give like an explanation also to the customer, right, as the EU requires, you better say, well, I estimated the behavior of my classifier, but I really don't know what are the bounds of this quantity I'm giving you, okay? So better to estimate this reliably, getting a bound, and if essentially we get 0 error, then we get exactness, okay? All right, another good motivation for tractable models is that, well, sometimes if you just sprinkle this structure over your model class, then you can be much faster than an approximate inference scheme, okay? So here is an example from a nice paper that essentially does compression. If you have a generative model, then you can use that actually to compress your data, compress and decompress your data, just by looking at the likelihood and using some clever algorithm, for example, arithmetic coding. And from this slide here, what I want to show is that these models here, which are the tractable models I'm gonna introduce in a bit, these PCs, these probabilistic circuits, compared to other generative models that are a bunch of normalizing flows and variational autoencoders cast into nice schemes for compression, can get you lower BPD, where BPD is the bits per dimension. You can think of like the negative log likelihood, rescaled, right? Essentially tells you how good you're fitting your data. But at the same time, for encoding and decoding your data, since they are tractable and then allow you to compute things exactly and very fast, they can dramatically reduce the time for performing this inference scenario. So the inference scenario here is yet another query, yet another function you want to compute. But if your model is tractable with respect to that query class, a model class, you can do that much, much faster, right? So this is like one strong point of view. And another like motivation is that, for example, if you want to solve scenario number 3, which was certifying that model is robust with respect to some adversarial examples, if you want to solve that pesky expectation there, for example, by sampling, then you need lots of samples. Actually, many, many samples if you want to provide some guarantees, some bounds over that expectation, right? So if I really want to get like 99.99% confidence interval, that what I'm computing is really that expectation there, I need lots of samples, okay? And for a fairly small neural network, the number of parameters is here, I will need to compute millions and millions of samples and pass them through my GPU. I can speed this up, of course, and try to parallelize, but I need to compute that a lot of time, and it will take still, let's say, 10 seconds to certify a single input for that neural network, which is very small, 90 million parameters. However, if that kind of similar neural network adds some structure, and we're gonna see how to do this later on today, then you can essentially do the expectation exactly in a single pass. And then, of course, this scales much more gracefully, okay? So the bottom line is that if your model is tractable for a query class, then you might get that just computing the quantity you care about can be very fast, okay? But more generally, another argument for tractable inference is this one here. So I would argue that we always do tractable inference on some approximate model class, okay? So sometimes we design this model class in advance, but some other time we start from an intractable model class and we want to perform inference on that model class. What do? We need to transform the intractable model class somehow in some tractable form and use that to operate with. Otherwise, there is no way. Okay, so for example, you have been exposed to variational inference, right? So if I have my intractable model class P, and I want to pick like a tractable distribution Q, maybe you have seen like the mean field approximation, right? But this can be something even fancier, like a normalizing flow or whatever, that is tractable for computing a joint distribution. Then, essentially, I'm going to use this as a surrogate to provide inference. So I'm going to learn something that is tractable, that is as close as possible to my intractable model. So I'm going to do exact inference for the quantity that I care over an approximate model, hoping that the approximate model is close enough to the intractable one, okay? But in general, even if you do sampling, right, in this case, we translate a big intractable integral or a big pesky summation into a much simpler sum that we can compute. So this is just like a sum that I can compute like easily, right? And then we say this is going to approximate this, and we have a super nice theory, as you saw this morning, okay? So the bottom line is that whenever we want to compute something, ultimately, we need to get our hands to something that is tractable, to a tractable model. Even if it's not a probabilistic model, it's just like a tractable function, but we still want to do that, right? So whatever I'm trying to say is, understanding where we can build something tractable will help us always, even when we deal with intractable models and approximate routines, because we need to put our hands over something we can compute exactly at a certain point, okay? All right. Any questions so far? No? Good. So the question becomes, well, I want some tractable formalism, right? I want to operate over some tractable model, maybe just because I want a super expressive variational family, such that I can approximate better my even more intractable, but perhaps even more expressive probabilistic model. How do I do this, okay? Or I just have like a reasoning task, a query at end that I want to solve very fast, right? But I also want to be expressive, right? So what do I do? So it seems like there is a trade-off between tractability and expressiveness, okay? Whatever I'm going to show you in this first part of the talk is giving you some recipes to navigate this landscape and try to draw a trade-off, try to sort of like connect the points such that you can find like a middle ground when we can have something that is tractable but also very expressive, potentially, okay? So this is a cartoon, and just imagine that this is a cartoon because, as I said, this is a spectrum, so tractability cannot be easily defined. It really depends on the classes of queries and classes of model you care about, right? But I'm going to give you this 2D cartoon representation to still build on the intuition why we would like to do this, okay? So on the x-axis, I'm going to put farther on the left models that are less expressive, where less expressive essentially just means that you might need like a larger model to represent a function that you care about, okay? And more expressive means like the model should be, let's say, small, okay? So here it's a little bit subtle because many of the models I'm gonna show you, the circuits and the mixtures even, just a mixture of Gaussians, they just do inherit the same properties that an MLP has, for example, and technically, they are universal approximators of densities, in the sense that for a mixture model, the more components you add, and then you can approximate arbitrarily well any density, okay? But then it's just like an asymptotic argument, so in the limit, okay? So this is not essentially what we want, because we deal with representations that are finite, and then we can squeeze on the GPU. So something that's infinite doesn't fit my GPU yet. And then on this axis, I'm going to put something that is more tractable here and less tractable here, where more tractable, again, is just an approximation to say a model class that might be able to solve multiple queries, multiple reasoning scenarios efficiently and exactly, okay? So here is the cartoon. So many models that are based on composing neural networks in an arbitrary way, like flows, VAEs, GANs, diffusion, that you have discovered or revised these days, might be very expressive, they're very flexible, but might not be tractable. So you might need additional routines like variational inference or sampling to try to compute quantities of interest that is doing reasoning over them, okay? Classical models instead, like simple mixture models, shallow models like Gaussian mixture models, decision trees, HMMs, and very simple PGMs, they don't seem like to compete with deep learning, modern deep learning, in terms of expressiveness, right? But they can be very tractable. In many scenarios, many quantities you can compute exactly. And if you think about this, for example, many of the things we can do for Bayesian inference or even for the fusion model yesterdays were essentially relying on the super nice properties that very simple distributions like Gaussians do have, or mixture of Gaussians, right? So that's the power. We need them, and they reside on this quadrant here. But in the other end, how can we sort of like navigate this space here and move from here to here and pass by this quadrant here? This is where we would like to be. How do we do that? Well, one possible way is that if we use some of the ingredients that old school models have, but we pump them on steroids, that is like we over-parameterize them, we give them many more parameters, and we make sure they run on the GPUs, and essentially we train everything by SGD, then in a sense we might say, well, they're using the deep learning recipes, you have 1 billion parameters, you have the structure of an HMM, but we have 1 billion parameters, so you are more expressive, you can fit more things, but still retain the nice properties of tractability, okay? The other way to navigate the spectrum is to go the other way around, right? So take some of these architectures and impose more structure. In a very analogous way, these models are doing. And the structure is gonna help you compute these quantities of interest, okay? So this is what I'm gonna try to describe in the next slides. Essentially try to build a framework of very simple computational graph that are gonna tell you what are the structural properties or the way to over-parameterize good old-fashioned models such that you get a nice trade-off in between expressiveness and tractability, okay? All right. So here's the plan. Can we design these computational graphs that efficiently encode the inference like in the classical PGMs? So I'm gonna start from a very simple model that you have seen here in the course a couple of times now, and perhaps you already know. And if you don't know, it's still good to revise that, okay? And these are like Gaussian mixture models. Super simple, they are a staple in machine learning, they are a workhorse, and they are so elegant and so beautiful, okay? So here's a super simple, one-dimensional Gaussian mixture model. I'm just taking one Gaussian here and another Gaussian here, representing here their densities, right? So this is one density, this is the other density. Each one is parameterized by its own mean and its own variance. And then I'm putting them in a convex combination. So these two weights here are positive and they do sum to 1. Okay, and what do I get here? I get another density here. It's already normalized because this is normalized, and these two sum to 1. And this is like this strange orange shape here. And why this strange orange shape is better than the two single shapes? Because it has like a strange bump here. It's definitely not Gaussian, so you get something more interesting. And it's also a little bit more bimodal, okay? So this is the nice recipes of mixtures. So you take two simple distributions encoded here by their two densities, right? They're fairly simple. Then you put them together and you get something more interesting. And in this case, you get a bimodal distribution, okay? Now, I want to take the super simple model and want to translate the way I use it to compute inference, compute quantities of interest here, even just the density, like in this case, into a data structure, essentially a computational graph, okay? So here's the computational graph. It's something super simple. Here's my input variable, x1, the only variable these two Gaussians are defined on. And here I have two neurons. You can think of them like some custom functions, some custom computational units you can write like in PyTorch or JAX, or if you really want, TensorFlow. And then use them, essentially parameterize them by their own mean and variance, right? And each one of them receives, for example, a particular value, a particular real-world instance of x1, and then just outputs the PDF of that specific Gaussian, okay? And then you just introduce a sum unit that is weighted, and these are the weights that do appear in your Gaussian mixture model, okay? So here's the super simple computational graph. So how do you use it? How do you use the computational graph to just compute this quantity, this PDF of the Gaussian? Well, you just have to compute this formula here, which corresponds to a feed-forward evaluation of the computational graph. So for example, I would like to understand what's the density of x1 equal to 1. So I plug in 1, I feed 1 to this Gaussian unit. The Gaussian unit is gonna output 0.06, for example. The other one has a different mean, a different variance, so it's gonna output another value. Then I multiply the values, I sum, and I read out the value, okay? It's a super simple computational graph that just tells you that you can do a feed-forward evaluation of a graph and then get the value that you would have computed. There's a question. Yes, please.
So how do you do this to not, what if the variable is not infinite? What if you have a continuous variable?
Can you say that again? Sorry.
What if you have a continuous variable?
So the question is, what if you have a continuous variable, right? But this is a continuous variable, right? Because it's a Gaussian.
But then how, so if I look at the graph here, you have 0.8, 0.2. Then what if you have too many categories, too many situations that you want to include?
Someone says when you have too many situations, you can include. Can you give an example? What do you mean by situations?
So now you have the probability that x equals to 1.
X
is actually a Gaussian distribution and you want to represent all types of x.
Someone says, what if this is a Gaussian distribution and you want to represent all types of x? But let me clarify, this is a Gaussian distribution, and here I'm evaluating not the probability, which would be 0, this is the density. Okay, so the x can take all the possible values on the real line, right? And this is, you plug it 1, what's the density evaluated at 1? You read out this Gaussian, you read out the Gaussian, and you combine the PDFs. Then with the same computational graph, you say, what's the density of x equal to minus 3 point whatever, right? You plug minus 3 point whatever here, you read out the PDFs, then you sum, and then you... Yes, I'm computing the density. Yeah, so just to recap, right? You have a distribution. You can encode the distribution in many different ways, right? If you have just discrete variables, you can have a mass. If you have continuous, you can have a density. If you have mixed continuous discrete, you have a mixed mass density distribution. You can use the characteristic function if you have access to that. You can use the moment generating function. These are alternatives to encode the distribution, okay? But you can use all of them and actually represent them in computational graphs. But for now, I'm using continuous variables, and so I'm using densities, PDFs. Other questions?
How do you learn for multiple x? Like here we are doing this v1 x equal to 1. So how do we learn?
So the question is, how do we learn this distribution when we have multiple x's and I think like multiple data points? Well, how would you learn with a neural network? So first of all, let's define what are the parameters. So the parameters that you might learn are the parameters of the mixture, plus the parameters that you have inside every Gaussian, right? You have a mean, and you have a standard deviation or variance, depends on how you parameterize that, okay? If I have a data set which comprises a single feature, because I have many x's, right? How do I get these parameters such that my model is closest to the data? I will do maximum likelihood, okay? So I try to maximize the likelihood of my model given the training data, okay? One way to do this, since this is a simple computational graph, is let me just compute the negative likelihood. I want to minimize it, and I want to backpropagate through the graph and just update according to the gradient, right, these parameters. If you have a neural network, right, and you want to train the parameters of the neural network, you just do SGD, given a proper loss. Yeah. As long as this guy here is a neuron and it's differentiable, right, with respect to its parameters, then you can backpropagate and learn the parameters. So you can learn a Gaussian mixture model by doing expectation maximization, but you can also do that with stochastic gradient descent. It's going to be slower to converge, but it works. And once you see this perspective, then you will say, well, SGD is more natural than EM. I just represent my GMM as a computational graph, and then I just like backpropagate through that, okay? Other questions? All right. Now, a note on notation. So from this slide on, I'm not gonna represent this additional node that was here, the input, x1, and connect that to the two different Gaussians, because it becomes very messy later on to connect every node to all the features it's defined on, okay? Instead, what I'm gonna say, I'm gonna just use this additional label to say this Gaussian here is defined over my feature x1, and this other Gaussian here is defined over the same feature x1. I call this notion the scope of the unit, okay? So I simply say like, the scope is the set of features every function encoded in my computational graph is defined on. So this unit has scope x1, this unit has scope x1, and this unit has scope x1 because like it's a function defined over x1, okay? I'm also gonna drop the arrows because it can be messy to draw them over and over. There's a question, yes?
Maybe you're gonna explain it later on, but this question about the weights, because in this specific case, they're constrained to sum to one. So how do we force it in one?
So the question is, the weights in a mixture are constrained to be sum to one. How do we do this, I think, in practice when we implement it, right, and when we do SGD? Well, options. What you can do is that you can reparameterize them by a softmax, for example, right? So you have some unconstrained real values, you pass them through the softmax, and then you get like values that sum to one, and then when you backpropagate, you just update everything. That's a possibility. All right. Okay, that was one dimension. Let's go to higher dimensions, right? So I still have a Gaussian mixture model. I still have two Gaussians here. They are multivariate Gaussians, however. So I'm mixing them here. And what I'm representing this here, this is the covariance of one Gaussian component. This is the covariance of one other Gaussian component. And with the colors, I'm essentially saying that they have a block diagonal structure, essentially implying that some variables here do not interact with some other variables here. So all these blocks should be null, while they do interact here. And for the other Gaussian, you have still relationship of this kind, block diagonal, but with a different set of variables, okay? Essentially, for a Gaussian, I'm saying that two different subsets of features are independent, okay? So I can rewrite my Gaussian mixture model in this way. This is the first component, but the first component factorizes in a smaller Gaussian defined over only the blue variables, and the red Gaussian defined over the red variables. And the other component factorizes in a different way over the yellow and over the green, okay? So these are local factorizations. Every Gaussian factorizes differently, okay? And then I mix them together. How do I represent this as a computational graph? I need to introduce another unit, which is the product unit, okay? And the product unit just encodes this product here. So here's my first Gaussian defined over the red, other Gaussian defined over the blue. I do the product of their PDFs, right? And I do the same for the other component, and then I mix them again in a sum. So I still have like two components in my mixture, but every component factorizes into smaller Gaussians. Okay, still multivariate though. Okay, so these are local factorizations. So these variables, they're independent at this level, but then when I mix them, they become dependent. Okay, question?
Yes, so the product of the Gaussian is still going to be a Gaussian?
Yes.
So the advantage of doing that decomposition would be, what would be the advantage?
So the question is, product of two Gaussian PDFs is going to be still Gaussian PDF. So what's the advantage of this? Well, it's definitely going to be a Gaussian PDF. In this case, they're actually defined over these joint sets of variables, so it's even easier to just put them together in a Gaussian. The advantage is that we're going to repeat this process over and over and over and over in a slide or two, and essentially you're going to have many local factorizations, but mixed in a very intricate way, such that you can have like some hierarchical structure. At this level, you simply don't gain much. You simply say like, I observe that my data might factorize in this way.
Would it give a convolutional type effect? Would it, on an image, would it give a convolutional type?
Someone is saying, would this give a convolutional type of effect? I don't think so, because in this case, I'm dividing my set of variables into two disjoint scopes, right? I'm saying these two sets of variables are independent, therefore the joint PDF decomposes as the product of the two PDF. I'm not operating into doing the product over random variables. This is where perhaps I think your convolution idea might come from.
Does the CNN nowadays filter, how they create stacks of these filtered images?
The idea is it's even simpler. Imagine that you have like the filter, but then you partition your image in disjoint patches. So the patches are not overlapping, okay? Whenever they are disjoint, then you can claim that your PDF factorizes, or your mass factorizes, or your cumulative distribution factorizes, okay? All right. So I introduce another kind of unit. So these are the ingredients. Oops. These are all the ingredients that you actually need for this framework of probabilistic circuits or PCs. First of all, you need some units, I will call the input units or input distributions when I talk about distributions, that just encode some simple tractable functions. It can be a small Gaussian, it can be a small neural net if you're able to compute, for example, an integral over it. It can be a small normalizing flow, it can be a small VAE, as we're gonna see later, so on and so forth, okay? Something that is small, that's nice, compact, and tractable. Then I can do a mixture of these two by putting a sum unit. Or I can do a product of two of them, okay? Or I can do, as I just did before, a sum of some products, okay? So these two are locally independent and then get mixed into a factorization here. And then later on, I can go and create this hierarchical structure. So I can do a sum of some products of some sum of some products and so on and so forth, okay? So here you get an advantage, because if you try to unroll this, and I will show you this later, essentially you're going to encode a very large mixture model. It's like a mixture model with an exponential number of components, okay? But this you do just like a polynomial number of parameters. Yeah, you share a lot in the drag, right? So for example, you say like, I'm gonna put together this x3, this Gaussian over x4 with this with x3, right? And I'm gonna mix them in this way, but then I'm gonna also mix them to different one in this way, and then I'm gonna split again and mix and split and reuse and split and build it in a recursive way, okay? You apply these three rules and then yeah, someone is saying like, as long as just mix something, I get like still a distribution, a PDF, but now I'm doing this arbitrarily, so why do I still get my distribution? I'm gonna give you the properties in a bit. There was another raised hand, yeah.
How finely trained can we make this split up into, for example, the covariance blocks? Since we have like an upper block and a lower block, in principle we could recursively split it more and more. Is this some kind of limit or like some kind of...
So someone says, if we split all over again, can we have some structure in the covariance? And the answer is yes, but if you think about the covariance of a Gaussian, then you just need to do product splits. Because the issue is that whenever you mix two Gaussian distributions, you don't have like a Gaussian anymore. So you can come up with some covariance structure, right? But it's not like the covariance parameterizing the Gaussian, if this makes sense. All right? Okay. So here's a just slightly larger circuit. I put some values here, okay? And now I want to compute what's the density when I observe x1 equal to minus 1.85, x2 this value, x3 to this value, x4 to this value. So essentially I want to evaluate the joint density, okay, my joint distribution. How do I do this? Well, I just do feed-forward pass, okay? So I go on over my circuit, I look at the input distributions, and then with respect to the variables they are defined on, I just plug these values. For example, these two units here were defined over x2. Then I take like this value, 0.5, I plug this in, okay? And I repeat doing that for all the others. And then I keep doing like in a feed-forward way from the inputs to the single output, okay? And I just do sum and product, sum and product, sum and product, sum and products, okay? And I get the output here, which is 0.75. Okay? That's the value of my query. So I have a very simple query. This is, get me like the joint density. I want to compute that, and then I just evaluate the graph in a feed-forward pass, okay? All right. Now, why is this framework somehow useful or interesting? I'm going to give you 3 reasons. The first one is that with this framework here, you can represent a large class of tractable models, from mixture models to trees, even XGBoost, HMMs, other PGMs, as we're going to see, but also tensor networks, for example, which are another fancy name for exactly what I'm just showing you, okay? And for example, if you have a PGM, you can just compile that into a circuit structure in this way. What do you gain if you do that? Well, you might have a library that lets you do inference over PGMs, and it might implement some algorithms like variable elimination, as you saw like in the first day of this course, okay? Or message passing or something else. But if you want to compute something slightly more exotic, like, I don't know, some entropy distribution, some entropy of the distribution or other quantity, you might need to re-implement that, for example. Instead, if you just convert that to the circuit and you have routines that already do this over circuits, then you can do that in the new formalism, okay? So here's the conversion. You can get a tree PGM. I'm going to show you very quickly a way to build like the circuit. There are many other ways to do that, however. So this is a process called compilation. It's actually called bottom-up because we start from the leaves of the tree. So this is a very simple tree Bayesian network. And then, for example, I can look at this conditional distribution here. So A depends only from C. So I can introduce 2 indicator input distributions. And this is essentially going to be 1 only when this variable A is equal to 0. And this is going to be 1 only when it's going to be equal to 1, okay? And then I put them in a sum, and this I'm encoding the probability that A is 0 or 1, given that C is equal to 0, okay? And I'm going to read these values out of the CPT that I have in my Bayesian network here. I can do the same for A given C equal 1. And this will be another sum unit, and I just read out these values from the CPT. The moment you evaluate this small circuit in a feed-forward way, essentially you are just looking up values in the CPT here. I can do the same for B and implement the distribution of B given C. And then I can do the same, essentially building this up even more. So C given D, for example. I have to compute C given D equal to 0. I introduce another sum unit, and then I connect that, making sure that I have a switch here that connects it when C is equal to 0. And I just have to remember what are the previous units that were encoding this event. I do the same for C equal 1. And then I do the same kind of thing for C given D equal 1. And then I can just like put a single sum here. That's going to encode the distribution of D. And since D has no parents in my Bayesian network, I don't need to build the circuit anymore. Now, trust me, the circuit encodes the very same distribution you have in the Bayesian network. Now, if you want to do inference here, you just set properly the values of the inputs, and then you do the feed-forward pass, and you're going to get like the same value you're going to get in the PGM, in the Bayesian network, okay? If you try to do this by hand, then you will realize that the process that I did is essentially a version of variable elimination. I use variable elimination to do all the sum and the products and encode them in a data structure. Yeah. Yeah. So someone says, here, I'm introducing some units that are indicator variables. So actually, there are some degenerate Bernoulli distribution. You just have all the mass on a single event. Yeah. If you want to do this branching here and this conditioning, it is true that it will the circuit structure that I might build from the PGM might, given this procedure, be exponentially large if the tree width of the PGM might be very large. So for this procedure, this very special compilation that I give you, this can happen. There are other ways when you can exploit something else happening in the circuit, and I have a slide for that in a bit. All right. So the same exercise you can also do for an HMM, okay? Yet another 3 PGM structure that you can compile in a circuit in this way. But as I said before, once you have like this tree structure, right, from a PGM, for example, then we can over-parameterize that. So for example, instead of putting a single sum unit for a given scope, we can put many of them. And each one of them is going to be a very different mixture, coming with its own different parameters, right? So this is what we say when we say that we are over-parameterizing the structure. So we start from that kind of template, and then we keep on adding parameters, as many as you can fit in your GPU, essentially. And then you can also group them together and write them just like a tensor operation. So all these some units are going to have their own parameters, but you can group them in a matrix and just do some matrix vector product, okay? And these products here are just being some Hadamard product between this vector and this vector here. What I'm trying to say is that once you over-parameterize your circuits, there are ways to compactly put all of these vectors of distributions on your GPU, such that you can tensorize and parallelize even more. Okay? Question?
So maybe you said, what's the difference between the plus signs on the bottom right and the plus signs on the top?
There is no difference. So I'm simply saying that here you might have like a circuit that continues, right? And at a certain point you have many sums here. And here is another sum. So it's like in another circuit here. You can have sums at different depth of the circuit. Okay. So as a matter of fact, you can see that many tensor factorizations, if not all of them, actually you can write them as a circuit. So this is how you can bridge other fields like tensor network or hierarchical tensor factorizations and represent them in the single language. And this begs the question, perhaps it's connected to what people were asking before. So can I translate all PGMs into circuits? Are they really the same thing? Can I do something different? And the answer is that it depends. So basically no, okay? So what happens is that with PGMs, we know that if I want to do marginal inference, for example, they can be tractable as long as the tree width of the model is bounded, okay? But in a circuit, we can encode a PGM with even high tree width in a more compact way, because we can exploit a finer grain of independence, which is called context-specific independence. Okay, and what's context-specific independence? It simply says that two sets of variables are independent given a context. That is, given, for example, some events, only some values of another variable or set of variables, okay? So these two are independent whenever I observe Z to be equal to a single value, but whenever it's equal to a different value, they are not independent anymore, okay? So what this implies? Implies that you can do something like a decision tree. Okay, so whenever you observe some values for your variable, for example, then you can have two different kinds of probabilistic models. And in this, things might be independent, and here might be dependent, okay? And therefore, you can try to crack the problem in two different ways separately, and perhaps reuse the structure that's in both, okay? This is something that you cannot represent explicitly with the language of probabilistic graphical models. But you can, for example, for decision trees. And a decision tree of this kind, you can still represent as a circuit in this way, okay? All right. Then, another point of difference is that whenever we have continuous variables in a PGM, then it becomes tricky to represent or compile them into a circuit, because we will need an additional ingredient, not just sum and products, but actually a unit that computes an integral, okay? Because when we marginalize things, for example, in variable elimination or the sum product algorithms, then we will need to compute integrals, okay? So we need to extend the language of circuits. I cannot show you how to do this right now, but I'm going to point like to some nice paper that extends the language by introducing integral units. Okay, but all of this to say that many models, like tensor factorization, tensor networks, HMMs, mixture and trees, you can just represent them as circuits here. Okay, this is cool, this is nice, but how do they perform in practice? How expressive are they, right? Well, it turns out that the more you over-parameterize and the more we are being able to scale inference these days, we can be even competitive with respect to other classical intractable models, for example, like variational autoencoders. So this is a table taken from a small image dataset like MNIST, fashion MNIST, and all the other variants. And here we are reporting, again, the bits per dimension. So the lower, the better. And these are variants of circuits of some kind in different flavors. And these are normalizing flows and other variants of variational autoencoders trying to do compression, essentially. And at least on these MNIST kind of data sets, with circuits you can do even better. And you can exploit the structure of your images. I'm going to give you some example how to do this later and build your circuit. And at the end, you get a circuit that is tractable. Okay? Yes, please. So the question is, it seems like circuits are suffering from high dimensional problems. Can I, yes, convince you on ImageNet? So these data sets are actually outdated. So I might have even update this with a paper published at ICML this year, where results are even better. And so, yeah, okay. So one thing to keep in mind is that all the literature of circuits is sort of like lagging behind, let's say, at least let's say one generation behind like the other models, right? For two reasons. First of all, they are not as common as the other models, so you need to implement slightly different, right? And the community is also like growing, but it's not as large as all the other communities put them together, okay? So this is why you see like the deep learning community advances one step, and then the circuits advances, but the deep learning community also advances one more step. The bottom line is that these are from 2 years ago, and we were already able to scale to billions of parameters. So you can get like much better results. And if you look at the bits per dimensions of the latest works on RGB images, that they are essentially there or better. So we are right there. Okay. Yes, there are some. I can give you some pointers later. I don't have them in the slides. Okay, third point, why are they somehow interesting? And this is related to what I was promising at the beginning. So trying to chart the trade-off between expressiveness and tractability. And I think this is actually the real killer application, which is, if you really care about computing something tractably, which means either exactly, because you care about exactness, or you just care about doing things very fast, you can understand what are the structural properties needed to do that with circuits. This is the nice part, okay? So what are these structural properties? There are 4 main structural properties, and they have strange, weird names, like smoothness, decomposability, determinism, and compatibility, that definitely do not mean what you think they mean. So smoothness is not the smoothness that you think, okay? So it might be even easier for you to think of them and abstract away from the name for a while, okay? The important part here, the message I want to convey you is that if you have some of these properties in your computational graph, then you can guarantee that you can compute a query class exactly just in a pass of your computational graph. That's the important part, okay? So for example, if you have property A and property B, what you can do is that no matter how big the sum or the integral, you can marginalize any possible subset of your variables exactly and efficiently in a single feed-forward pass, okay? For example, you can renormalize your model. if you marginalize everything, or you can marginalize any subset of your pixels or images, okay? So what are these properties A and B? So the first one, called smoothness, is a property of some units. It essentially says that all the sum units encode a mixture, which means that they receive inputs from functions that are defined over the same set of variables. They do have the same scope. Here, instead, this might be a Gaussian or another circuit defined over x1 and another over x2. So whenever you define a mixture, you just put together PDFs or masses functions that are defined over the same set of variables. Doesn't make sense to have a Gaussian defined over the height and the Gaussian defined over the weight of people, and you sum their PDFs together, right? So that's smoothness, the property here. And all the sums I showed so far, they already define and they already satisfy this property. Property B, decomposability, essentially says the opposite, kind of, for product units. They do need to encode local factorizations, so their inputs should be defined over disjoint set of variables, okay? And this makes sense, because if I have like a disjoint set of variables, then I know that I can combine the PDFs, I can combine the masses, the CDFs, and I'm still gonna get like a valid distribution, okay? And note again, this independence assumption is only local. So whenever I put a sum on top, then things get mixed and dependent again, okay? So if I have smoothness and decomposability, I can solve any integral in a single feed-forward pass. For example, same circuit as before. Now I want to marginalize out two variables, x2 and x3, and just compute the PDF, the marginal PDF over these two. What do? I take these values for these variables and I plug them in over the inputs that are defined over these variables here. And for the other variables, well, I simply marginalize them in their input units. So if these were Gaussians, I need to marginalize over the Gaussian, but the Gaussian is already marginalized, it's already a proper distribution, so its partition function is gonna be 1, okay? So I just plug 1 here, okay? And then I just propagate these values in a feed-forward fashion. And at the end of the computational graph, I got my value, which is the answer to my query. Okay? Question?
For example, if I have a Bayesian model, and I'm interested in the likelihood or in the evidence of my data, then evidence is then I have to integrate out the weight, distribution of the weights of likelihood times prior. So if my likelihood times prior satisfies these two properties and can be represented as such, I can exactly
Yeah, so the question says, can I use this property when I want to compute like the evidence in a Bayesian setting? Well, as long as your joint distribution over the parameters and the data is a circuit with these properties, then yes. Then you can marginalize. In the Bayesian setting, the parameters are also random variables. So they should be also input, appearing as input over the circuit somewhere.
Yeah, because you said like the integral is tractable in the first two properties.
Yeah.
Is that like a reasonable assumption? Or is that like, can that somehow be
So the question is this like some properties that can play well in the Bayesian setup? Well, it depends. It depends on how.
is there some way so that you can validate that this assumption is
Well, I mean, if you assume that your model, which is something that we do usually, right? You write your own model, and you assume that the true distribution factorizes in this way, right? And that's this old structure. Once you assume that, then you are in business. If you build a structure of the graph with these properties, then you are in business. Right, so why does this work? Because just the integral breaks down over the structure of the circuit. It's a form of doing dynamic programming if you want. So imagine that you want to compute the partition function and integrate over all your variables. And imagine that this is like your circuit here. This is the output in red. This is a sum unit, and this is smooth, right? It means that the integral over the output of the whole circuit is the integral over this summation here, right? But I can just like swap the summation and the integral, and essentially push down this integral and solve two independent problems here that are smaller in a sense, okay? And then it's easier. And if my product is decomposable, then for example here, I know it's gonna be the product of three different things, and therefore my multivariate integral is gonna just decompose in the product of three different integrals, right? Each one defined over the scope of the different units here. And whenever I reach an input unit, we are saying that we're like simple tractable units that I can essentially integrate easily, okay? And therefore, doing this computation here gives you the sense and then the explanation why the feed-forward pass is valid and works. Now, if you can do that, essentially you can mask whatever set of pixels that you want, and you can marginalize them out, okay, because they're missing features. Or you can condition over any possible subset, and you can, for example, sample. But this is on MNIST, and I agree, like, it's not interesting, but then you can start doing this on much more interesting features, images, RGB, right? This is a nice paper from friends at UCLA, published like a couple months ago at iClear. And the property of conditioning over an arbitrary subset of your pixels is very beneficial if you want to do, for example, diffusion. Okay, so you can have a small circuit inside like a more complicated intractable pipeline where you have a diffusion model that helps guide the diffusion process when you want to do, for example, in painting. Okay, so you condition on a patch, no matter what it is, then you can do this tractably with the circuit. And then the circuit can help the intractable model. So it's a cool reference for you if you want to have look it. Okay, so for the first scenario, we need these two properties, property A and property B, smoothness and decomposability. And if we can do that, then we can essentially solve the task exactly and efficiently. But what about the other properties needed for other scenarios? Well, let's have a very quick look at the case of adversarial robustness, but we're gonna just reuse whatever I told you before, so it's a sort of like a refresher. So here's the quantity, the query I want to compute. I have my model F, I have the input X, I add some noise E, distributed according to some isotropic Gaussian, and then I get a new classifier, okay? And people essentially were saying that this new classifier can be certified in the sense that no matter which kind of noise you add to corrupt the example X, if this noise falls into this ball centered around X, the output of F is not gonna change. The output of G is not gonna change, okay? And as I said before, if we impose some structure over F now, okay, so F is gonna be our circuit, then we can try to compute this expectation exactly and scale, as I was showing at the very beginning. How do we do this? Well, imagine this is F, okay? These do not need to be distributions anymore, because this can be just like a classifier outputting a number, but they can be also distribution. The bottom line is that, again, if we start from the top, which is the root, and this is a sum, then this expectation, again, swaps with the sum, okay? And then here I am again needing to solve the problem for these other two units in a recursive way. Note that here I do not require the sum to be smooth, to be defined over the same kind of things, because I don't need the probabilistic assumption. My probability distribution is defined over the E, the noise only, okay? So no matter what, this expectation is still gonna be well defined. And then if I have a product, again, in the very same way, I can essentially decompose the expectation in the product of 3D expectations here. And keep on doing this until I reach the inputs, and the inputs are small enough. For example, a one-layer neural network with ReLUs, you can actually compute this expectation in closed form efficiently. So for that, you can have like small neural networks, one layer, one hidden layer defined at the inputs, and then putting on top a circuit structure, okay? And if you do that, essentially you are orchestrating the inference of the small MLPs. Okay, so for this you actually need just decomposability. All right, so what about the fairness case and scenario? This is essentially a generalization of this other example here, because we do have a trickier expectation when the P, the distribution, does not factorize very simply like isotropic Gaussian, okay? And yet, if you select the P and the F in a certain way, then you can still compute this integral in closed form. The question for me becomes, which kind of structure do I need to impose on P and F such that like this function, this integral, can be computed exactly and efficiently? Well, we need the other property called compatibility. And compatibility is a property defined over pairs of circuits, like in this case here. In a nutshell, compatibility says that all the product units that are in this circuit, on this one and in this one, if they do have the same scope, if they are defined over the same sets of variables, they decompose in the very same way. Essentially saying that whenever I'm going to push the integral down, the integral is going to exactly split in the very same way for both of them. And therefore, I can split the integral for both P and F. This is at a very high level. This will essentially tell me that we can compute this integral in time that is upper bounded by the size of P times the size of F. And this is a very loose upper bound. But if this size here you can fit on the GPU, and this also you can fit on the GPU, you can kind of think of like a quadratic increase in size, right? And therefore, whatever you need to fit is like the kind of like squared, but it's not really squared. It's like squared in every level, in every layer for this one here. And then you can exactly compute this efficiently. So here's just like an intuition of why you have like this quadratic effect here. If you have a distribution here, which is just a simple sum, it's a mixture and it's shallow. But then you have a second one, which is another mixture with another number of components, right? And if you want to do the product of them, the product is still a mixture, right? But you have a quadratic number of components here. Now, if these guys here decompose in the very same way, which is essentially what compatibility gives you, then you can push the integration down after you swap with the summation. But you have to take care on this Cartesian product of the local mixtures. Okay, so this is the goal for now. I will try to speed up, but if you have like questions, just stop me, right? Okay. I just realized I'm incredibly late and over time. All right, so this was like the initial panoramic examples to show how structural properties do map to certain inference scenarios that you can solve tractably, which means exactly and efficiently, okay? Then there was this lonely property here, property D, determinism, which doesn't mean what you think it is. I do not have time to tell what determinism is, essentially. You can find the references about that, but let me just tell you that if you also add determinism, you're gonna encode more structure in the model, you're gonna restrict its expressiveness, however, you're gonna increase its tractability, because for example, you can do tractable map inference, which means in this context, you just maximize for any given set of your variables, okay? And if you can do that, actually you can compute other interesting quantities, like the entropy, for example, and this can give you a tractable elbow for some interesting families, like log densities, right? As shown in this nice work by Stefano and Andy. Okay, what I want to go at is that structural properties do tell you which kind of queries or query families you can solve exactly and efficiently, okay? But there is one issue here, is that potentially this nice matrix here, even if it has like a finite number of rows, what are these structural properties, it's gonna have an infinite number of columns, okay? Because you can always come up with a new mathematical quantity you want to compute, and then what do? How do you build a circuit? What's the structural property that you need? You can try and do that on Scratch, but can we somehow do this in a systematic way? And the answer is yes, for many queries that you can build by composing them composing some simple atomic operations, okay? Let me give you some intuition why this should work. So for example, if you have these queries as before, so what's the expected prediction of a patient? So you have an expectation, or you want to compute the variance of that prediction, right? So you have to do some more computation here, or computing like the fairness, for example. All these mathematical expressions are actually made of the same building blocks. You have to compute these pesky integrals, then you have to do some products, then for example for the variance you have the power and things like that, okay? So what I'm gonna say is that now I want to build an association between structural properties and just computing these single atomic operations. If I'm able to do that, then I can very quickly get for free tractable algorithms for all possible combinations of these operators, okay? So here is my language. I'm gonna look at all the queries all the mathematical expressions over probability distributions that I can compose by using the sum, the product, the power, the logarithm, the exponential, and the quotient, okay? This is of course not all possible mathematical quantities, but it's interesting enough, for example, to represent many divergences and information theoretic kind of quantities, okay? And I'm gonna do this in a higher order computational graph that is a computational graph that operates on computational graphs, so operates on circuits. What's that? For example, this is like my Kullback-Leibler divergence between two distributions P and Q, and here is its mathematical formula, and this is how I'm gonna write that in this way. And every operator, atomic operator here, takes some circuits, some computational graph with certain structural properties, and outputs an intermediate circuit with other structural properties, okay? So for example, I do the quotient between the two distributions, and I get another circuit R. Then I take R, and I do the logarithm of it, and I take another circuit S. Then what I need to do to compute the KL, I need to multiply S with P, all right? And then get another circuit T, and then I integrate these out. Okay, so essentially I'm rewriting my query as a bunch of like intermediate operations where these operations are coming from a dictionary of possible operations, okay? And then I can do this for the Kullback-Leibler divergence or other divergences like the cross entropy, which is a much simpler computational graph of this kind, right? I just do the log and then I do the product and then I want to integrate this out. All right, so essentially what I want to get is a kind of like Lego-like system where I add these blocks and I just understand whatever it takes to compute this block and what are the properties of the circuits that are input of this block and the properties of the circuits that are output of this block. And once I get this, then I am in business because I can stack all the blocks in the Lego language as long as the output of one Lego block is a valid input for another one, okay? So for example, as I showed you before, I can take a circuit, I can do their product together. We were doing this as long as they are compatible. And of course, they are smooth and decomposable. And if I do that, I know that the output circuit is gonna be smooth and decomposable, but also compatible with the previous two. Okay, this I can prove because I can write down a tractable algorithm that can do this in tractable time and give me a circuit that is compact at the end with these properties, okay? If I want to do the log, I've written down another algorithm that takes a circuit that is smooth, decomposable, and deterministic, where determinism is this fourth property. I didn't have time to explain in detail, and gives me a circuit that is smooth and decomposable. So it loses the deterministic property here, okay? But then, as long as this circuit here can be fed into another operator that accepts smooth and decomposable circuits, then I can stack the two blocks together, okay? So in a sense, the metaphor is this one. Think about having a function and having types over the inputs and types over the output of the function. And the types in this case are essentially coming from the structural properties of the circuit. So it's like you can build something like a probabilistic programming language where the types are the structural properties here. And what does this give you? Well, you can reason backwards and understand very quickly what are the structural properties to have a big tractable model that's expressive, but still tractable to compute the query that you have, you're considering right now. So for example, if you have the cross entropy here, and you can start backward from this circuit S, you know that you want to integrate that. But to have tractable integration, as I said before, we might want S to be smooth and decomposable, property A and property B. If this is the case, then I can integrate this, right? And then I can reason backward. What are the properties of P and R such that I get a circuit S that is smooth and decomposable? Well, I will need them to be compatible, right? So they need to be smooth and decomposable and compatible, and then I know that this is smooth decomposable and I can integrate. And therefore, I'm just left to understand what are the properties of Q and R. And as I said a couple minutes ago, then I want Q to be smooth decomposable and also deterministic. So if I put everything together, if I want like an expressive class of models for P and Q, they can be circuits that are smooth decomposable compatible, and Q is deterministic. And I can compute this exactly. If you repeat the process, then you can do that for many different divergences without having to essentially reinvent the algorithm from scratch every time. You just compose these blocks, okay?
This sounds amazing, and I'm staring at some of those divergences that are notoriously, I think, difficult to optimize. So with a strategy like that, so if I look at something like the Vergari, have you found that the optimization problem becomes much easier to do or in practice?
So someone says, some of these divergences are extremely hard to optimize. Do we get any benefit of representing the input distribution as circuits, or does the optimization benefit from this? I cannot answer systematically to this. I think there is no investigation about like the optimization landscape, but only in terms of expressiveness. So, for example, here, the divergence is in closed form if both distributions are circuits, and therefore, like, it's very easy to compute then. I cannot tell you if increasing the size of the circuit something changes, or if you over-parameterize, the landscape becomes hell. That I cannot tell. Question mark.
Can you say something about the concentration properties of the distribution you implemented that?
Not that I know of, but it might be possible. Someone was asking about what about the concentration properties. I think you can derive concentration inequalities based on this. A circuit should be a sub-Gaussian if this is what you're hinting at. Then we can talk later, perhaps, about
This mixed type can be multimodal.
So someone is saying like multimodality can be an issue, and I do agree. So details to be checked. Okay.
Are there roles which maybe show the conventional probabilistic models may be used for stochastic optimization, like RL or Bayesian optimization? Do these kind of probabilistic circuits provide an edge?
So the question is, do circuits provide an edge over stochastic optimization or Bayesian optimization? I think there has been a nice work recently from people at Darmstadt using circuits for Bayesian optimization. I can send you a reference later, perhaps. All right. Okay, cool. Yeah, so for example, here is how we will build them together with small functions and build the Lego pieces together. All right, so I will be giving you a couple principles on how to learn the circuits. So far it's been mostly representation, right? But this is also because the circuits are just computational graph and they are peculiar neural networks, so it's very easy, okay? So very simple neural network, you just do backprop. You do SGD and you learn them. End of the story, okay? This is the easy answer. It's also the convenient answer because you can reuse all the optimizers you have in your neural network toolkit. You want to use Adam or Adam W, and you can just use it, right? You don't have to reinvent the wheel. However, we can do a little bit better because, for example, it's also a hierarchical mixture, so a hierarchical latent variable model. You might want to use EM, for example, and you can do that. And EM is going to converge much faster, okay? That's something. To learn normalized weights, someone was asking before, how will we parameterize them? So for example, we can use a softmax, or we just like make them positive, and then renormalize everything in the end, because we can always compute the normalization constant with circuits easily, okay? So for EM, I don't have time to get into the details, but this is nothing fancy. This is the normal update rule for EM, when you want to essentially aggregate over all your data and compute the posterior probabilities of the latent variables. What are these latent variables coming from in the circuit? Well, if you think that every sum unit in the circuit encodes a mixture model, right? Every mixture encodes like a discrete latent variable, okay, that we are marginalizing out when we evaluate the mixture. So for every sum unit, you do have a latent variable, and you might have like this gigantic latent variable model that you can train by doing EM. And the nice thing with circuits is that this quantity here, which appears here, you can just compute by doing backprop. So in a single pass of a backprop, you can compute all the gradients you need also to do EM. So it's quite convenient. All right, there are also variants if you want to be Bayesian, such that you treat the parameters of the circuit to be random variables, and you can put a prior over that. There are a bunch of works trying to do this from a variational perspective, but also sampling perspective. I did, for example, one of these works by devising like a Gibbs sampler. And why that is nice is that because you can condition, right, very easily with the circuit. You can do the marginals, and then you can condition. And you can even raw Blackwellize your sampler, because you can marginalize many things at once, okay? In general, however, if you put like a prior over the weights of your circuits, you might lose tractability for some of the queries, okay? But some of the computations needed to do a nice, efficient sampler might still come up from the structural properties of the circuit. Okay, in general, these days, this is how we learn the circuit actually. We build a template, and this template is called the region graph. So it's not really important how it's called, but it's important what it encodes. Essentially, this is a DAG that we build in certain ways. I will show you how to do this later. But we take all the variables that we have in our data set, and we try to split that somehow. So this is a template that preserves the structural properties of the circuit, and specifically decomposability. Okay, so that's the important part. And once we have this template, we go into every region here, every set of variables that we have here, and then we populate that with units. And then we have many choices, because how the way we put the units there corresponds to a local factorization. So we can get essentially help from the rich literature of tensor factorization. You can put a factorization that is a canonical decomposition. You can have like a Tucker decomposition or fancier versions, okay? And you just need to connect the units, and by the fact that you are following in this template, you know that the set of variables is gonna be split into two disjoint set of variables, and therefore decomposability will be satisfied. At the same time, you can decide to put many more sum units here and here, and have many more connections, and this is the overparametrization thing that helps you, okay? Then we can have circuits with lots of parameters, and you just learn the parameters. How? As I said, by SGD, any of its variants, or even EM, okay? So how do we build these region graphs? They can be quite intricate, and we have several routines to build these templates such that they respect decomposability, right? One way, for example, for images, is going to be trying to split the image in many different ways according to a certain pattern, right? So this is perhaps related to what someone was asking before. Essentially, does this relate to convolution in a certain way? There is no direct connection, but if you allow for disjoint steps where you move the kernel, right, and then they never overlap, then you get something similar. You can start from the full image here, and then you can decompose that. For example, you can partition that in a vertical way in this piece and this piece here, or in this piece and this piece, or horizontally in this piece and this piece, or this piece and this piece. And then you can keep on splitting all these pieces, right? And reusing the previous piece, because at the end, you're gonna end up with just like the small patches that, however, you are reusing over and over in a kind of like recursive way, okay? So this is a very intricate region graph that you can build. And then for every region, which is a bunch of pixels, which are your features, you can decide how many units you want to put. And everything is gonna be essentially smooth and decomposable. Or sometimes you just like build this template in a random fashion, and still it works. This is the no learning option. But most of the time it works. So why does it work? Because in a sense, it's the overparametrization. So if you have enough kind of parameters to wiggle and to fit your data, then you can do like an interesting job nonetheless. Okay. All right, to conclude this, which was supposed to be the first part before the break, shame on me, then the bottom line is that there is a whole trade-off between tractability and expressiveness, right? And whatever you want to do in probabilistic reasoning, it's better to be aware of that, right? Such that you can pick the right model for the right task at hand, okay? I'm giving you a framework to understand this trade-off a little bit better, okay? And this is a framework where computational graphs are simplified neural networks where you are allowed to put and connect something by preserving certain structure. By preserving structure, you get the tractability, and by over-parameterizing, essentially you increase the flexibility of the model and its ability to capture what's in the data. Okay. Right, so what matters is structure. So other questions on this part here before I move to the actual second part? No? All right. So, all right. So I will try to go very quickly to this part here, and essentially saying that whatever I showed you so far, but whatever also all of us lecturers have talked about so far, is trying to design and try to perform inference over generative models or probabilistic models in general that encode distributions, that encode uncertainty. And we want to do this because the data that we get is uncertain, right? We have noise in the measurements, we don't know exactly how things go, and whenever we want to make a decision, we want to have probabilities also because probabilities inform us on the uncertainty that is on the inputs or the outputs of the model, and tell us this uncertainty needs to be taken into account, okay? So probabilities are super important. Some of you might hear at a certain point from Turing Awards, they say, like, you don't need probabilities, you just need energies. It's not true. You need probabilities. In any case, it's also true that sometimes some events are certain, right? So you might not want to have a probability that is different from 0 and 1. The trick is, how do we incorporate this in our probabilistic models, okay? Because it's extremely challenging. Even if probability theory should, in a sense, it is a generalization of logic, which should be instead like the science telling us that something is either true or false, either 0 or 1, okay? So how do we mix these kind of things? Well, and why do we need that in the first place? Because some scenarios do need a single answer, right? We do not have uncertainty over that. For example, when we do mathematical reasoning, we know that the answer comes, it's the output of a deterministic algorithm. And we would like machine learning models and probabilistic models also to do that, right? Happens when we do like a summation, happens when we want to prove theorems. So some events are certain in math reasoning. They're also in physics law, right? So we know, for example, when a reaction happens, when we have some constraints that are, for example, preserving the number of atoms, the number of electrons, and so on and so forth. So this is something that happens in physics, and we would like to impose that in our machine learning systems. And more generally, when we have constraints that we design as humans, then, for example, we would like the AI agent to satisfy the constraint, because some scenarios should have like probability 0 because it's a scenario that is unsafe, okay? So whenever you have, for example, self-driving cars, many of the systems do come with a small components that comes with deterministic rules, okay? All right, so we want to include this in our machine learning systems. What's the issue here? The issue is that whenever we have a statement in logic, the statement is an indicator function. It's a function that takes some values as input, but the output is essentially 0 or 1. For example, you have a statement, if x is a bird, then x flies. You can represent that in some logical formalism here. For example, this is the first property over x, implies that b is true for x, okay? And this is something that can be scary for someone, but whenever you see a logical formula, just think about an indicator function, okay? It's something that outputs 0 or 1, okay? Or alternatively, think about a function that is stepwise, or it's like piecewise constant, okay? Some regions of your space is going to be 1, all the rest is going to be 0, okay? This is where the tricky part comes in, because we want essentially events that have like 0 probability. To transition from logic to probabilities, we have probabilistic logic. In probabilistic logic, we don't talk about simply a logical statement, but we talk about the probability of a logical statement. So we would like to understand what's the probability that this function is actually 1, okay? Dealing with this requires that we need to be careful when we engineer our systems, and sometimes it's hard with the models that we have in deep learning. For some reasons I will touch in a bit. But for now, just let me give you some cases, some showcases, where neural networks are having a hard time dealing with these hard constraints. Logical formulas are hard constraints, okay? So when we have to deal with logical consistency, sometimes LLMs are very inconsistent. So they have a hard time trying to understand if they assert that something is true, that the same thing negated in natural language should be false. Negation is extremely tricky to perceive, for example. Implication and all other variants and multi-hop reasoning are also quite challenging. Just adding more data doesn't seem to help consistently across, okay? But this is just logical consistency. If you want to reason and do something more involved, for example, planning, then you will need to keep track also of different other states, of the uncertainty, also things that you do not know, what are your current goals, and things like that. So planning is perhaps the most challenging task that very big and promising and successful ML models like LLMs are facing these days. So this is a position paper by Rao. I put it up a couple of months ago. That's an interesting read, just to get a feeling of how this reasoning task involving some form of logic and hard constraints might be challenging. Okay, even generating valid molecules seems like to be challenging and still open. We were discussing with Wouter the other day, for example, and it's tricky, right? So sometimes we are very good at generating something on our benchmarks, but if we look at a little bit more closely, we might see that something is not exactly perfect, or the molecules that we generate do not satisfy some constraints, or they cannot be synthesized because they don't make sense from a physical or chemical point of view, okay? So there was this fancy sentence said like many years ago by Ali Raimi, saying like deep learning is doing alchemy. And if we look at the reaction, sometimes it's true, because deep learning systems do substitute some atoms. For example, some selenium atom in the molecule, they make it like into sulfur at a certain point without realizing it. And if this were like a nuclear reaction, that would be okay, but sometimes it's not a nuclear reaction, so it's not exactly okay, right? So why all these constraints are challenging? And I'm not going to give you a definite answer to do this, but just showing some special cases where this becomes easy. But what are the issues? Why this is tricky? Because first of all, they come in a different number of shapes and forms, and then finding a single way to put them together in all our machine learning systems is very tricky, okay? So as I said before, we might have like some plans, or we might have some paths, logical formulas for hierarchies. How do we represent them all together? How do we make them play well all together with probabilities, right? And when it comes with probabilities, you can think of them as sort of like soft constraints, right? So you want the probability of some statement to be too old, but it's extremely hard in the way we train deep learning these days, which is essentially treating everything as an end-to-end differentiable machine to enforce that your probability distribution, no matter how you parameterize, puts a hard 0 to some events that violate the constraint. So it is true that probabilities do generalize these binary events, but then training them and making sure that you recover that is extremely hard with the differentiable machinery that we have these days. And when I say differentiable machinery, I also, as a computer scientist, need to be a little bit careful, because whatever we say in deep learning these days, something is not differentiable. Sometimes it's better to be translated into, well, it might have gradients, perhaps everywhere, except some points with measured 0, where we don't care. But the point is that the gradients are useless. That's the non-differentiability sometimes we mean when we say something is not playing well with these functions. So I said before, a logical formula is a piecewise constant function, for example, right? And piecewise constant functions, well, they are differentiable almost anywhere, everywhere. The issue is that the gradients are 0, and they're not really helpful if you want to use the gradient to tweak your parameters. Okay, so this is a partial view, a partial solution of a very large umbrella field. This can mean many things. This is probabilistic neurosymbolic AI. Essentially taking the probabilistic reasoning that you have experienced in many flavors, not just like the exact variant that I tried to introduce so far, but also all the nice approximations you've seen all these days. Try to combine them with neural networks, right? This is already something that we do when we have probabilistic classifiers or where we have like Bayesian neural networks. But the missing ingredients is essentially make them play well with our constraints, okay? So this is what I'm gonna try to do for the next 30 minutes, trying to give you some partial solutions for this very hard and challenging modeling problem, okay? So here's my goal. How can we make these neural networks learn and reason when we have these logical formulas, these symbolic constraints, hard constraints? And we want to do this reliably and efficiently. So what do I mean by reliably here at this point? I would say that if I have a neural network, right, that makes some predictions, I want that the predictions are guaranteed to satisfy these symbolic constraints, these hard constraints that I care about, okay? For example, if they encode safety constraints, I don't want the neural network to output something that violates the constraint. And when I say efficiently, for these contexts, I mean that I still want to use all the deep learning machinery that I usually do in deep learning, okay? So I want to compute gradients, I want to train my deep learning pipeline end-to-end by doing maximum likelihood, okay? And therefore I want exact gradients. It's possible to do something alternative, for example, approximating the gradients, trying to have other learning objectives that are non-maximum likelihood. But as a probabilist, I will say, like, let me try first with maximum likelihood, and let me see how far can I get, right? Satisfying this reliability and efficiency constraints. So here's my goal for the next slides. Okay, and then again, we have the logic versus the probabilities. I need to be a little bit more precise, because logic can be many things, okay? So there are different flavors of logic, and of course, lots of theory and research around that. So for example, there is propositional logic of zero-order logic. You just have the connectives, but all of these symbols here, you can treat them as binary variables, okay? Then we can go to first-order logic when we have quantifiers and we have predicates over the variables. But the variables can be something more than just like binary values, for example, or discrete values. And then we can start moving to the continuous, and then have a special case of first-order logic when we have, for example, constraints. There are algebraic constraints, like in this scenario, okay? All of this, the more you go down, the harder it is to make it play well with probabilistic models. So for now, I'm just gonna stay at this level here, and it's already challenging, okay?
Sorry, so how do I go from one order to the other?
So for example, how do I go from here to here?
Yeah.
That you can start having like quantifiers and saying something like olds that exist one variable, or this holds for everything, and you have like predicates and you have like functions. Or, and then at a certain point, then you can pick, for example, in SMT actually a theory. Let's say the theory of the linear constraints over the real variables, and then these are real variables, and then you can have linear constraints, and you just play them together with connectives like disjunctions, implications, negations. So for example, here you can encode a polytope if you have many hyperplanes and you say like all of these should hold in their intersection. But if you put a disjunction, then you have a collection of polytopes. But for now, I'm gonna pick like the simplest scenario, okay? All right, so here's what I want to go to. So I want to take a neural network architecture. This is gonna be a classifier. I have an input, many variables, and I have an output with many outputs. So this is going to be structured output prediction, like multi-label. classification, I want to encode my constraint into the last layer and then make sure that all the outputs do satisfy the constraint. And everything that does not satisfy the constraint has probability 0. Okay? And I'm going to use this running example here, which is a fairly toyish example from the neurosymbolic literature, but still it's very good to show how hard the task can be. So your input is essentially a bunch of bitmap images taken from Warcraft maps, okay? This is your X, okay? A bunch of pixels. And then you want to find essentially a path from this point here to this point here. And this is your output Y, which is a vector of binary variables. And what are these binary variables? Well, you have to imagine that over this image, you can overlay a grid. A grid that, for example, is done by 16 times 16 small edges like this, okay? And every edge in the path, or every edge in the grid, actually, is encoded in this binary vector. And this binary vector, essentially, you find a 1 if the edge is in the path, it's active, okay? Otherwise, you find a 0. So for example, this path here is going to be encoded as a sequence of 0 and 1s into this Y, okay? So that's your Y, and this is my task. I want to get the argmax. I want to get like the best label that maximizes my conditional distribution, okay? This is my output and this is my input. But I don't want any possible configuration of the edges in the grid. I just want those that make a path, okay? So here is my constraint. So this is my constraint. And for those of you who are not familiar with this notation, this means like that this vector of 1 and 0s satisfies the constraint. And the constraint is a complex logical formula, but written in propositional logic, okay? You can think of this as a filter, okay? Some of these configurations do not make sense of 0 and 1s because they do not encode a path, okay? Those that do encode a path, then make the expression, this logical formula, evaluate to 1, okay? So if I do have a 12 by 12 grid, my vector Y yields 2 to the power of 12 by 12 possible states, okay, which is a big number. However, only, double quotes here, 10 to the power of 10 configurations of Y do make sense because they are valid paths. They do satisfy the constraint, okay? So I want to build a neural network that, given some image, outputs a binary vector, and the binary vector always makes sense, always encodes the path, okay? This is one variant of the problem. Another possible variant is that you have your X, which is your generic table in your data set. You have a bunch of features, right? And then you have like many Ys, many labels. For example, they can be objects or genes or expressions. And over these labels, you have a hierarchy, okay? So you know that, for example, some of these labels are a superclass of other labels. And some labels are a subclass of other labels. What does this imply? It implies if you see some instance that has a certain subclass that is true, then also the superclass should be true. So for example, in logic, it means that if you have a label for the cat, you see that there is a cat in your input, then the label for animal should also be true because cat is an animal. And if you see something for a dog, then you should see something also for an animal again, okay? Whenever you have a hierarchy, if this is true, then the superclass is true, and then the superclass is also true. Or if you have preferences, the constraint is that your preferences should form a valid rank, okay? So in X, you can have, I don't know, some partial preferences of a user trying to pick some sushi, okay? So you only observe k minus n sushi types over all possible k sushi types, and you want to predict the rest. Okay, but the rest should still be a valid ranking. A valid ranking means that you cannot have like the same ranking and you associate to the same ranking to different sushi types, or you cannot put the same sushi type into two different positions. Okay, how do we structure the neural network? But for our problem here, it's not super important. It can be anything here that maps an input to an output, but at a certain point you have some embeddings here and you consider only the last layer. Okay, so if you have to use a deep learning framework or even something from sklearn, since this is multi-label classification, what people would use 90% of the time is just assuming that all the y's are essentially conditional independent given the x, or better, given the last layer embedding that you have here, okay? The reason is why people actually say, well, the last layer makes this linear assumption, right? You just draw this bunch of hyperplanes for every label y, because the neural network here, the backbone, if it's deep enough, if it's expressive enough, it's gonna able to disentangle all my representation, and I'm gonna be able to linearly separate all the different labels. For every label, I can separate if it's true or false, okay? It's a very simple assumption, but we can do better, right? But so far, there is no constraint added whatsoever. So if we do that, and let's say your backbone is a ResNet, which is something outdated in computer vision, but still powerful enough for this kind of like super simple image data set, right? Even if you're able to fit the training data extremely well and do perfect reconstruction of the path for the training data, at test time, the ResNet is gonna have a very hard time. So it's gonna predict a vector of y, then when you visualize that, you're gonna see it's not really a path. So some of the edges are disconnected. So the solution does not satisfy the path. How can we deal with this kind of problem? Well, most of the time, the simplest thing to do that you should try to do is, can I somehow massage my constraint, relax it a bit, right? And add that as an additional term to my loss, such that I can help the model, guide the model during the learning process, such that it's gonna learn the constraint a bit, okay? This is a very powerful and widely used paradigm, adding the loss as an additional regularizer, right? And one of the most commonly used strategy for this is the so-called semantic loss, which comes in this form, and I'm gonna explain a bit why it comes in this form. But essentially it tries to say, try to maximize a bit the probability that the constraint is true. Okay, I'm gonna give you some intuition why this is gonna help so far. It builds on a task that's called WMC, weighted model count, and essentially computes the probability of our logical formula. So this is what it's inside the logarithm of the semantic loss. Essentially, you're summing over all possible states y and computing the probability of y if this is your logical formula, your indicator variable, if the state satisfies the constraint, okay? This is just like the expectation of this indicator variable, which in turn is just the probability of your logical formula, okay?
When we do it this way, we end up with a single loss value, right? So we add everything together, let's say. What is the advantage of encoding it this way and not choosing a multi-objective criteria?
So someone says, what's the advantage of encoding this as a loss and not having like a multi-objective criteria? What do you mean by multi-objective?
For example, I can optimize for loss to have like the lowest loss value, but at the same time I could optimize for the highest amount of constraints that is fulfilled, and I can make a score out of it, so to say.
Well, this is what it's happening here in a sense, right? So this is your normal loss. Let's say it's your cross entropy, right? You tried essentially just to match all the entries in the y with respect to your ground truth vector, and then you add this additional loss term. So you do have a kind of like multi-objective scenario, if this is what you mean.
The reason I'm concerned is that usually these losses are not guaranteed to be like in the same kind of ranges, right? Or like in the same kind of value ranges.
Oh, yeah.
How do we, it's just a parameter that controls everything.
That's the simplest thing you can do. You can do better, probably, but this is like the solution that's commonly used. Yeah. All right, so we want to compute, we want to force the model to give assignments to things that satisfy the probability, satisfy the logical formula, and therefore like maximize the probability, okay? And what do they do, actually, many of these works, is doing essentially the same that the sigmoid layer from sklearn or some other PyTorch architecture is assuming that is independence, okay? So all the y's are assumed to be independent here, and this is the default assumption that you can do, okay? We would like to have something that is more than just this product here, because keeping track also of the correlation between the y's is important. And also, if you don't do that, optimization becomes trickier. There is a nice paper published at ICML that analyzes also the landscape of this loss when things are essentially independent. But even if you do this, okay, and you pick like the semantic loss, you do a much better job at test time, but if you look closely, might not be perfect, right? Because it's just a loss, so you don't have guarantee that you can essentially encode all the labels, and then they need to satisfy the constraint. So how can we do that? Okay, how can we make sure that the path is always going to be a path, or the ranking is always going to be a ranking, or the output hierarchy, it's actually always going to be a hierarchy? Well, this is the architecture. This is the last layer, and then you're done. Okay? So what happens here? Well, this is your input, this is your output, okay? This is the penultimate embedding, okay? Or if you want, the last embedding before the last layer. You have two components here, the blue one and the yellow one. The blue one is essentially an expressive distribution over your labels conditioned over your input, but the condition over the input comes through the embedding, okay? So you take the embedding, somehow you have a function g that outputs the parameters of this distribution, okay? You can assume that everything is independent again, like in the previous cases, but you're not required to, okay? So this is your expressive distribution, can also be unnormalized. And then you have the second component, which is C. C encodes your constraint. So C encodes your indicator variable, okay? Your indicator function, sorry. So this is the constraint. The constraint might be defined over the output or also over the input, okay? And this is 1 only when this configuration satisfies the constraint. It's 0 otherwise. So what are we doing here? I'm taking like a distribution. I'm multiplying by a function that is 0, 1. Essentially, I'm cutting its support, okay? Something very simple. And this is something that goes under the name of product of experts. So you take two distributions and you multiply them together. In this case, this is not really a distribution, it's a little bit of a degenerate distribution because it just gives you 1 and zeros. But in a sense, think about you can renormalize that and then it becomes like a nice distribution, okay? Why did I put a sad smiley face here? Because a product of expert generally is intractable in the sense that you can do the product, but then how do you renormalize? If you don't renormalize, you cannot do maximum likelihood estimation, you cannot compute exact gradients, okay? So what I'm trying to do instead is let's find a way in which we can do that, in which we can compute the partition function, okay? So I can renormalize this. And note that this is like the partition function that depends over every input. So this is why I want to compute this efficiently. I don't want for every input to approximate or doing something different from that, okay? So this is my partition function here. As you can see, this is extremely similar. That's the weighted model count. That's exactly the weighted model count I showed you before. This is the probability for the configuration, and this is like the term, the indicator function for my logical formula, okay? Now, the question becomes, how can I pick a Q? How can I pick a C such that they are expressive models and then they yield a tractable product? And that's, I'm just going to reuse whatever I showed you in the first part, right? And the answer should be like some circuits with some structure. And what's the structure here? So the structure is that I want to do the product, so they need to be compatible, okay? This is something I already showed you before. And whatever I'm computing here for the partition function is just like their renormalization constant. And I know I can compute that if these are compatible, okay? Now, how do I model this actually in practice? Well, this is a little bit a strange circuit because it's parameterized by the neural network. So all the layers of the neural network up to that are actually giving an output the parameters of the circuit. What are the parameters of the circuit? All the weights that were associated to the sum units, plus all the weights, or let's say the parameters, are associated to the input distributions. Okay, so the neural network output this. So for every different input, you're going to have a different parameterization, but the structure is the same. And therefore, the structural property is the same. And therefore, you know you can compute that in closed form. And for the and for the C, the yellow part, the constraint, well, the interesting part here is that the logical formula can also be compiled into a circuit. Okay? And the very same kind of principle that I showed you to compile a probabilistic graphical model into a circuit applies here. So you can take a logical formula and turn that into a circuit, okay? And the input of the circuit are going to be these degenerate Bernoulli distributions, indicator functions, that have all the mass associated to a single value. So for example, if this is like your formula, you start from the input. This is like a bottom-up approach, slightly different from what I showed you before. And therefore, you introduce like an indicator for y1 equal to 0, or y1 equal to 1, the same for y2, and so on and so forth. And then, by reading out what you have in the logical formula, you can start adding sum and products. And note that the sums here actually can encode the OR in the formula, but it's a special kind of OR. It's actually XOR, because these events are mutually disjoint, right? And then you can start building the circuit. For example, adding the product whenever you have the end, and the end is defined over this disjoint set of variables because we want decomposability. And in the end, you get a circuit that encodes this logical formula here. So if you set the values that you observe for all the variables, the output is going to be 0 or 1. Depending on the fact that the input satisfies the constraint or not. And then you can do, again, the product of the two. So this is a very simple kind of recipe, piggybacking over all the theory and the representation I showed you before. So you take the logical constraint, you compile that into a circuit in this way, you multiply that by the other circuit Q that encodes this distribution, and the distribution is parameterized by the neural network, and then you train everything end-to-end by SGD. Okay? How good are they? Well, here are some super simple path problems and the sushi ranking problems. And since it's multi-label classification, you can have like some exact match accuracy. So if all your labels match exactly, or just keeping some more relaxed version like the Hamming distance. But the bottom line, where I want to draw your attention, is that all the solutions, when you employ this layer here, this semantic probabilistic layer, are always going to be consistent, no matter what. They might not be the best solution, but they're always going to be consistent. So you're going to boost the normal accuracy in terms of exact matching, but the important part that they are going to be consistent. So for example, in this scenario, this is the ground truth. You don't recover the ground truth, but you still get a path. Even if you do the semantic loss, you can get something that is better than not doing the semantic loss, but still it's not a path. So in this way, the bottom line is that your task at end is cutting the support of a distribution and then renormalizing. If you know the theory, which structural properties you need, then you can do this easily. But then you can do, question?
Yeah, so I'm wondering, this example, so it's from Warcraft, right?
Yeah.
Which is from the 1995 or something like that. So how do they code the Pathfinder?
It's a super nice paper from people from Tübingen. They did it in 2019, I think. So I think they have a generative model that does some clever rejection sampling. So they have a generative model for the terrain, and then a generative model for do the path, and they want the path with the shortest cost, because I didn't mention, but whenever you move over the water or over the terrain that is a plane or whatnot, you pay a price. Essentially. So they created the generative model and they do some rejections until they generate only things that do make sense and they are the shortest path, and they have all this data sets which is available online. Yeah. I can give you the precise reference.
Yeah, I'm really curious, right? Because the technology that works must be somewhat old.
Yes, but I think what they're using is some, lovers of the game also build on top of that, and then you can have like generators for the maps.
Right.
So it might be that even these generators are old, but they are reusing them, and yeah.
I'm thinking since it's so small, you could probably just do a stat or a stat algorithm.
Oh, definitely. I mean, all these path kind of things you can do without the neural component. That's for sure, right? Why do we do this? Well, in neurosymbolic, the underlying assumption is, can we build a model, and perhaps a model that is end-to-end differentiable, that learns to reason, or in this case, learns to find the path. Definitely you can do this, you saw with Dijkstra, shortest path. Does it make sense? Okay. All right. Okay, so based on these principles, then I'm gonna go very fast over some possible applications that use the very same machinery in neurosymbolic, okay? And even if they don't explicitly mention circuits, but if you look very closely, they use the very same machinery, okay? So whatever I told you so far, it's not very specific to a certain problem, but you can do something different and perhaps something even more interesting than just doing paths over Warcraft images, okay? One first task from ICML last year is steering the control, essentially controlling the generation of sentences with large language models. So your constraint in this case is a logical formula that tells you that, for example, condition on a prompt, you should generate a new sentence that contains this token or contains this other token and does not contain this token, and so on and so forth, perhaps in this order or whatever other tokens in between them, okay? Why do you want to do this? Because control generation, it's important. You might want to generate some text that is non-toxic, for example, so you want to make sure that some tokens are not there. Or you want to generate something that follows some certain template, okay? Because you want the LLM not to be too creative, to put in these terms, okay? So what they're doing here is essentially having a tractable model, which is an HMM, but an HMM you can turn and compile that exactly into a circuit, right? And then cleverly multiplying that with a logical formula that gives you the constraint, okay? So kind of like the same ingredient here. Once you know and you see what happens, then you know why do these applications work, and you might get also some intuition how to apply this for your scenario. Another nice application is in reinforcement learning. There is this notion of shield. So a shield should be something that should prevent your agent from taking an action that violates the constraint, okay? And then again, this shield is made through some form of logic, okay? And the same very machinery that I showed you also applies in this scenario. So you have a probabilistic model that associates some probability distribution over all possible actions you're gonna take, but some of them are not safe, so are not legal, they do not satisfy the constraint, and therefore they should have probability 0. Okay, you can try to do this also for improving the consistency of LLMs with whenever they try to generate something, right, or try to answer if some implication is true, then it better also generate that the reverse implication, if you know modus tollens, should also be true. And same applies for negation and combinations of constraints. Or you can also show that you can have constraints over other forms of knowledge bases, in specifically knowledge graphs, and you can help deep learning models that are trained over knowledge graphs to predict things on the knowledge graphs and be much more precise and consistent and do not violate some biological assumptions. So I'm gonna show you a little bit from this work from last year from my student Lorenzo. How many of you know what a knowledge graph is? Okay, a non-zero fraction of the people, that's nice. But for all the remaining ones, here's a knowledge graph. So it's another logical formalism to represent a piece of knowledge. You have nodes that are entities, okay? And then you have connections that are labeled, and these are relationships. So for example, you might know that some drugs, like ibuprofen, can be used to treat some symptoms, for example, pain. And loxaprophen is another drug that treats pain in the very same way, okay? So nodes represent entities, and they're also typed. For example, in this fragment here, which is a fragment of a real-world knowledge graph called BioKG, you can have drugs, proteins, symptoms, and functions, okay? And now you represent like a knowledge graph just as a collection of triples. Essentially, you serialize all the edges. For example, you have the loxaprophen treats pain, it's a triple of this scenario, okay? So you take this, the starting node, then the label of the arrow, which is the relation type, and then the ending node, you put it at the end of the triple, okay? And you keep doing this here. The first element of the triple is called also the subject. The second element is the relation type, right, or the predicates. And the third one is the object, okay? So sometimes we say we have like subject, relation, object triples, okay? And then you connect all the edges that you have in your knowledge base. You can represent that graphically like this, or just like a collection of triples in this way. Now, these knowledge graphs, they collect knowledge that we do have, but they are extremely incomplete, okay? And the most important, and perhaps even the simplest reasoning task you want to do on knowledge graphs is link prediction. That is, you want to understand if there exists a link in between two entities, okay? So you might ask this question here. This becomes your query. What does loxaprophen interact with, okay? So you assume that there is an edge, that is a relation, and the type of the relation is interacts, and then you say, what's this, the object, if this is the subject, okay? This is called link prediction, and that's the simplest reasoning task you can do with knowledge graph. You can do something even more complicated by doing multiple ops, right, and more complex queries that are subgraphs. But let's just stick to the simplest reasoning task ever for now, okay? How do we solve this with deep learning? Well, we have super simple models. They are still state-of-the-art in many tasks. And these are called knowledge graph embedding models, or KGE. What do? Essentially, they do associate a score function to a triple made by a subject, a relation type, and an object. And the score is just like a scalar in R. It's a value that tells you, in a sense, what's the strength of the connection, okay? You can think of the score as a sort of like negated energy, in a sense, even if people don't necessarily think of that from a probabilistic point of view. They are different kind of models. They have fancy names. Some of these names are actually the names of the tensor factorizations they do encode. Why do they do this? Essentially, they assume that all your graph here can be encoded as a very big tensor, but this tensor has many missing entries. So the task here is to compress the tensor into a bunch of like matrix multiplication and tensor multiplication, such that you can reconstruct the tensor and then predict the missing links. Okay, for example, one of the best one, which is actually the default solution that you find implemented and the people go and use most of the time, is just called CompX. And complex associates embedding that are complex embedding. So you have like a complex vector associated to the subject, a complex vector associated to the relation type, and then conjugate complex vector associated to the object. And what it does is just like doing trilinear product. So you take like the three vectors and you do the product element-wise, and then you sum. Okay, you do this in the complex space, and you essentially just take the real part out of that, and that's the score that complex associates to every triple. So how do you do link prediction? So essentially you score all the possible completion, and you pick one that has like the best score. Okay, so this is actually what complex does on this real-world KGE. It says that the best completion for this is going to be phosphoric acid. Okay, that's actually the triple that is associated to the highest score. Okay, but there is an issue here, and the issue is that this violates a constraint, and the constraint is that in this knowledge graph specifically, drugs can only interact with proteins, right? So if you know that your relation has a specific type, and this type is interact, then you can only have like as an object proteins. You're not allowed to have anything else. So the bottom line is that all the possible solutions that violate the constraint should have probability 0. Okay? This is not the case. And that's not the case because the model is not aware of the constraint, okay? It's trying to learn the constraint somehow from the training data, but in many cases might fail, okay? So the real solution is actually that Loxoprofer interacts with COX2, which should be a protein. Okay, so how can we sort of reuse the same machinery that I showed you so far also in this context here, okay? Well, I need to start with circuits or something that looks like a circuit somehow. And it turns out that all these models here, all the score functions of these knowledge graph embedding models, they do encode some form of circuits. They just don't output probabilities. So my job is trying to tweak them a bit and try to make them output something that is positive, okay? And I can renormalize, it's a probability. But they are made of the same ingredients. They're made of computational graphs that have products, and products here, and sums here, okay? They just have a slightly different kind of structure. Now, after we made this observation, and then we turn them such that the output are positive, then we can use essentially the same kind of machinery that I showed you so far. So if I have now a new score, which is a valid probability distribution, and that's the score of my probabilistic circuit here, of the subject, relationship, and object, it's gonna put some probability mass over configurations that do not make sense according to the constraint. But that's okay. I can still multiply that with another circuit that actually encodes my logical formula. So my logical formula says that only drugs and proteins should interact. And the logical formula essentially is gonna put this probability for the event that does not satisfy the constraint to 0, essentially. So I take a circuit, I take another circuit, I build them in a way I know they are compatible, I multiply them, I get another circuit, and this circuit is going to encode the constraint. So this triple here, or if you want this event, that the Loxoprofer interacts with phosphoric acid is going to have probability 0.
For these constraints, they seem like mostly binary constraints. Are we also thinking about imposing like priors for unlikely combinations, but then we might still want to allow? Or is this really like just a way of filtering out all the impossible?
Other questions? So the question is, how do we do the multiplication in practice? So there is an algorithm to do that does that for you. The bottom line is that the algorithm operates in a fashion such that since the circuits are compatible and all the product units decompose in the very same way, essentially you can have the circuit, the final circuit, that respects the same structure, and then every layer might have a size that is quadratic. It's essentially the product of the sizes of the other two layers, in worst case. But that's an algorithm that does that.
Just a curiosity. Here, every constraint basically adds a complexity to the final graph, right? So in this example, if you have more than one of these constraints, for example, in the chemical domain, so you have plenty of these constraints, do you think that adding more constraints will how is the correlation between the growth of the graph and the number of constraints? But also how complex then could be also the back propagation in a way that is because once we have not one, multiple constraints.
So the question is how complex becomes the process when you add more and more constraints, and how big becomes the circuit after you compile that into, after you take the constraint, compile into a circuit and do the product, right? It depends on the structure that you have on your logical formula. Sometimes you have logical formulas that even if you put them together, once you compile them, the size does not grow much. In other cases, the size grows a lot, and it can even blow up sometimes. So it really depends on the structure, the prior structure that you have in your constraint. So I cannot give you a super easy and clean-cut relationship between the number of constraints that you put together.
Maybe a silly question.
So someone is saying, if you just have a neural network, can we just like mask the output or filter the output to satisfy the constraint, for example? Maybe. Let me just say first something. This is actually, the graphic might be misleading in a sense. You're not just multiplying, or maybe you are multiplying here, but this is like your large, super large tensor that you don't represent explicitly, because this tensor here has 3 dimensions: number of entities times number of entities times number of relationship. And number of entities can be in the millions. Okay, so I'm never materializing this explicitly. I just have a circuit that outputs the value for every cell, every entry in the tensor. Okay, this is a graphical depiction that says like this is how the tensor might look like, but you never represent the tensor explicitly. These circuits and tensor factorizations allow you to implicitly encode this very big tensor without materializing that explicitly.
But like for a particular test input, we would have the output, maybe like you mentioned that if the CNN is probably long enough, then we can assume that we have done all the descent manually. So can we just put a constraint matrix on the last layer? So
That you can try to do, but then how do you train that? Because if you simply have, for example, this is a distribution, and then you multiply that by a mask of 0 and 1s, right? It's not a distribution anymore in the sense like doesn't sum to 1 or doesn't integrate to 1. If you want to do maximum likelihood, you need to renormalize. You might want to do something different than maximum likelihood, doing some contrastive divergence or training that as a product of experts in a different way. You might be able to do that, but you need to design a new learning routine.
we need to make the network aware that we have a constraint matrix at the end so that
You don't, not only that, you also need to redesign your learning pipeline. You cannot just use SGD and backprop. Okay. Right, final, I think like still late, but I will try to squeeze all the last slides in 10 minutes very quickly. So everything I showed you so far is essentially something that uses all the beautiful and elegant formalization of mixture models, okay? We have a very large mixture model encoded in a very compact way, and by these structural properties, we do have this tractability sort of like emerging very nicely, okay? And this is a rule that I think you should keep in mind. Whenever you are dealing with some distributions and something is working for that distribution, but you need something more expressive, then start looking at mixtures of that distribution, okay? Because adding components together, it's gonna give you a boost in expressiveness, okay? That's the mixture recipe to do things. And this is actually very, very popular, such that I can predict with very high probability, and you will see this at conferences, after you go at conferences after a while, if someone does a probabilistic model, okay, named A, someone else, perhaps the same person or someone else, later on, not soon after, is gonna do a paper about mixture of that model A, okay? And this makes sense, because mixtures are super, the simplest thing you can do to increase expressiveness and still retain kind of like the same properties. Something might break, but generally something keeps, still holds, okay? So that's the mixture recipe. So for example, if in your projects you're using Gaussians, starting or thinking, can I use like a mixture of Gaussians instead, okay? Right, where do circuits enter this picture here? Well, because a circuit, it's actually a very big mixture model. So as I said before, every sum unit is associated a latent variable, and therefore, this is like a hierarchical mixture model. Whenever I need to sample, I can select one input branch coming from in the sum unit, right? And therefore, I can color all possible trees that are these sub-circuits that I create here. And I can rewrite the whole circuit here as just a single big summation here over all possible trees. And how many trees do I have? Well, if you do the math, you're going to see that you have an exponential number of trees, exponential in the depth. But this is just like the normal deep learning recipe. The more layers you add, then you can have like an incremental, an exponential way to represent essentially all the possible combinations of the inputs, okay? So this is how you can rewrite a circuit as a very large mixture model, okay? With a number of components that is exponential in the depth of the circuit. But the number of parameters you're training is still polynomial, it's still very compact, okay? So to complete the picture, whenever you think about mixtures, you can do the next step and think, if something works for mixtures, then it's very likely that it's going to work for a deeper mixture model. And that is a circuit, essentially. But instead of representing this exponential mixture model in this way, then you can represent it in a compact way in this scenario, okay? All right. So another showcase of this principle. Well, people have thought, for example, well, VAEs work very well and they're very popular. Can we use them and put like a circuit on top, essentially having a hierarchical mixture of variational autoencoders? What do you gain by doing that? That at the inputs, you're going to have much smaller VAEs, so training them should be easier, and they will be less data hungry, for example. Okay, but so far, all these mixtures that I showed you, they do come with the very same recipe here. I'm just adding something, and more crucially, whatever I'm adding, I can only add. And that's because all the weights should be non-negative here, okay? That's the classical recipe we are being taught in school books for mixture models. But mixtures, technically, they don't need this, okay? The only requirement is that the ultimate value needs to be non-negative, and we are able to renormalize that, okay? And why we might want to do that? Why we want to relax that constraint that the weights have to be non-negative? Because we can be much more efficient in the way we represent our model. Here's a cartoon. So there is the donut distribution, right? And imagine you want to fit that with a Gaussian mixture model. If you start with 2 components, there is no luck. You need many more components to start doing a decent job, right? You need many small blobs and putting them here to try to fit the model. And this is because you can only add components. You cannot subtract components. But ideally, right, the ideal solution for this is I have a larger Gaussian here, and then I subtract a Gaussian from the center, okay? And I just represent with just 2 components this distribution, if I allow for negation, okay? Now, what's the issue here? If you just subtract PDFs, you might end up with something that is negative, okay? So it's not a valid density anymore, so you need to be careful. But if you're able to make sure that if you add subtractions, the subtraction is not going to disrupt your final distribution, your final density, then you might gain also expressiveness. And it's actually possible to prove that even a shallow mixture with some negative parameters can be much more exponentially more compact. You need much less components to represent essentially some functions, and much more compact than a deep mixtures with just positive weights, okay? How can we do this? How can we encode a subtractive mixture models, and in our case as a circuit? Well, what we do is we take a circuit here that can even output something negative. It's not important, so these weights can also be negative, and these functions might not be input distributions, can be whatever functions that you are able to integrate, but they're still giving something negative. So the weights here span the whole real line. And then you square it, okay? If you square it, then you make sure that the output of this square is always going to be non-negative, okay? And then you can renormalize, essentially. If you expand that a bit, this is the same machinery that I was writing many slides before this one. And now these combinations of the weights can be negative, can also be positive, but they are also negative, right? And then you can subtract mass. So you can be much more efficient in representing your distributions, okay? So this works for shallow mixture models, if I write them in this way. But how do we do this for a much deeper circuit. That's the open question. But let me also point out something, that we have a quadratic number of components, but only a linear number of parameters, just the original parameters that we are learning. These are all shared. But now you can subtract probability densities and mass. Well, we can just apply all the operations that I showed you before, right? So I multiply a circuit with itself. Therefore, if the circuit is compatible with itself, then I can square it, and then I can renormalize it. And that's it. So that's another application of using these properties and going even beyond the classical definition of mixtures that we've been taught in the book. And then I think we still have a couple minutes for questions. It's the same machinery that I showed you before, right? The square is also a circuit that's smooth and decomposable. So the normalization is a big integral or summation. And then I can do in a single feed-forward pass after I multiply it by itself.
Can you just show it for the simpler example in which you had two donuts, in which you had a donut? How about the long edge?
Like here?
Yeah, maybe here.
Well, imagine you need to normalize this one here. So you have the integral of this summation. You push the integral inside, and then you have to do the integral of this product here.
And that would be just the integral of individual probabilities.
Can you say that again?
That would be integral of individual probability distribution, whatever we choose, C1, C2, and C3.
So yes, these are simple functions, might not be this C, might not be even probability distribution. Imagine that you have some polynomials, okay? You multiply some basis function or polynomials, you get another polynomial that you can integrate efficiently, for example. Does he?
So we have, it's in a way, kernelized method of negative mixture, negative.
Can you say again? Go back to the Warcraft, the results. Versus losing, sorting? Sorry.
Losing performance.
Okay.
So basically, some don't quite indicate that there's no trade-off. Sometimes it's improve, but sometimes the decreased performance well if you suppose there's a trade, even though you gain consistency.
So someone is saying it seems like there is a trade-off between consistency over the of the outputs, right, with respect to the constraint, and some performance. But how do you measure performance?
Like in the case here, like you said, the path is kind of not very much. Not this one, it's the next one.
Yeah.
Yeah, no, the next one.
This one.
Yeah. So like the LSL produce better path that's not consistent.
Yeah, but the issue is that this is not a path.
Yeah.
Yeah, so if you compute, let's say, the Hamming measure, right, you're going to look if whatever single edges match with the ground truth, right? So, for example, if you do the Hamming score, of this and this, this matches, this matches, this matches, this matches, this matches, so you have a high Hamming score, right? But, for example, you have a 0 exact match, or it's not even a path, right? So someone is saying, can you relax consistency and try to explore solutions that are even not consistent somehow, but still are good according to some metric? Well, I guess this is what the loss gives you, in a sense, because you don't enforce consistency at inference time. The bottom line is, however, do you care about consistency or not? That's I think the underlying question, right? So it really depends if in your application you want all invalid predictions to have probability 0 or not.
Well, if you build an application that count a fraction on the right edges compared to the right truth, is there a way to convert so that
You might, but it really depends if you design your loss or you design your probabilistic model based on the requirements that you have, right? So you might need to come up with some application when you say, I really want only, I don't know, 50% or 70% of my partial solution to satisfy the constraint. I don't know if this makes sense, and I cannot think on top of my head of an application, but perhaps there is an application of this. If this exists, then I will start looking into ways to encode this perhaps first into a loss or later on into a layer. And perhaps you can have, I don't know, some probabilistic guarantee that the partial constraint is satisfied with high probability, maybe.
these are mutually exclusive, right? Either you impose a loss, a semantic loss, or you do SPL.
Well, yeah, in the sense that, I mean, here, you already are doing something that is very similar to what you're doing here during training. All right, thank you.